Hello, and welcome to The Shy Scientist, the place where curiosity gets cozy and science drifts at a gentler pace. Tonight, we're strolling through one of life's most puzzling companions. Time slips away without asking, shapes our days, and sometimes teases us, like when a kettle refuses to boil. But before we dive in, tell me, where in the world are you right now, and what's on your clock? Fitting, isn't it? We're all meeting in the same now, but scattered across different hours. If this little journey helps you unwind, a like and subscribe would mean the world. It helps others find this pocket of calm, too. Now, let's settle in and wander into the strange ways we feel time. 10 minutes in traffic can feel endless, but 10 minutes with a good book, gone in a blink. The clock ticks at the same pace. The difference is in your brain. Psychologists call it subjective time, the personal, often slippery sense of how long things last. When we're bored, with nothing to focus on, our mind notices every tick. But in a lively conversation or a creative flow state, we forget the clock entirely. Novelty plays a role too. Childhood summers felt longer because each day was packed with new memories. As routines take over, our mental highlight reels shrink, and years seem to speed past. Fear can stretch a moment, joy can shrink it. Some people in intense situations recall events in vivid slow motion, not because time slowed, but because their brain captured more detail. Different cultures even think of time differently. English treats it like currency we spend or waste, but other languages imagine it as a landscape. In some traditions, the future is behind you, unseen, and the past is ahead because it's already known. Inside us, a 24-hour circadian rhythm runs our daily cycles, while shorter moments are measured by a neural stopwatch involving parts of the brain like the basal ganglia. It's accurate enough until emotion, distraction, or multitasking throw it off. Why does the return trip often feel faster than the journey there? Familiarity. Your brain already knows the path. And the famous snooze button? Those 9 minutes feel like nothing because your half-awake mind isn't keeping score. Time, as we live it, is far more than numbers on a clock. It's a shifting blend of memory, attention, and feeling, bending with our mood, our culture, and the stories we tell ourselves. So as we drift between seconds and centuries tonight, maybe the best way to spend time is to simply notice it right here, right now. Time can rush past in a heartbeat when we're in love, stretch endlessly when we're afraid, and sometimes disappear without a trace. Physics might one day define it perfectly, but our personal sense of time will always remain wonderfully unpredictable for as long as we've existed. Humans have tried to capture this invisible current, from shadow-casting stones to machines that can measure a billionth of a second. Let's step back and see how we got here. Long before wristwatches, people looked to the sky. The rising sun, the drifting moon, and shifting seasons became the first calendars. Nature's clock, free of batteries. The ancient Egyptians refined this with towering obelisks acting as giant sundials. Their hours shifted with the seasons, but it worked for farming, prayers, and daily life. Then came water clocks, simple bowls or jars that let water drip at a steady pace, marking time even after sunset. Some were surprisingly intricate, with gears and bells that announced the hour. Across the ocean, the Maya tracked celestial cycles with astonishing accuracy, creating calendars that spanned thousands of years without a single cog or spring. In medieval Europe, mechanical clocks began to appear. Huge, tower-mounted machines that rang bells for monks instead of showing faces or hands. A breakthrough came in the 14th century with the Verge escapement, a clever mechanism that made timekeeping more controlled and portable. By the 1600s, Christian Huygens' pendulum clock brought accuracy down to within a minute a day, a leap forward that changed navigation, science, and daily life. During the age of exploration, precision became survival. To solve the problem of finding longitude at sea, John Harrison built the marine chronometer, a rugged, ship-ready clock that transformed navigation forever. By the 20th century, quartz crystal technology replaced swinging pendulums. Electric current made quartz vibrate at a steady rate, giving clocks and watches unmatched reliability at low cost. But the ultimate leap came with atomic clocks, using the vibrations of cesium atoms to define the very second itself. If one ran for 100 million years, it would be off by less than a second. Accuracy that keeps GPS, banking, and the internet in sync. From sun shadows to subatomic pulses, our tools for marking time have grown ever sharper. Yet no matter how precisely we measure it, time still feels personal, tied to our memories, moods, and the rhythm of our days. Maybe that's why we started tracking it in the first place, not just to schedule life, but to give it shape. A steady beat in the background, reminding us we're here now.
Al Newton's.
Time for Isaac Newton. Time was steady, universal, taking at the same pace for everyone, everywhere, forever. He pictured it as a constant river, flowing whether or not anyone was watching. This idea became the backbone of classical physics, letting scientists predict motion, plot, planetary orbits, and synchronize events with mathematical precision. But Newton's model came with an assumption that time exists on its own, independent of the things happening within it. Not everyone agreed. Gottfried Wilhelm Leibniz argued time was simply a way to describe the sequence of events. Without change, there's no time at all. Newton dismissed that, and for centuries his version ruled science, powering everything from navigation to train schedules. Still, cracks began to show in the 19th century. Experiments with light revealed something strange. No matter how fast you moved, light's speed stayed the same. This didn't fit Newton's universe. The puzzle lingered, till a young patent clerk named Albert Einstein stepped in. Einstein arrives in 1905. Einstein introduced special relativity, flipping Newton's steady clock on its head. He declared the speed of light was constant for everyone, and that meant time itself could no longer be universal. Two people moving at different speeds might not agree on when events occur. From this came the mind-bending idea of time dilation. The faster you move, the slower your time runs compared to someone at rest. Your light speed, your clock would tick more slowly, you'd age less quickly, and entire years on Earth could pass, while only months went by for you. This wasn't fantasy, it was physics. And it marked the moment when time stopped being the same for everyone, revealing that the universe's clock was far more flexible than Newton ever imagined. Time in motion, scientists have tested Einstein's strange predictions, and the results are real. In one famous case, atomic clocks were flown around the world in airplanes. When compared to identical clocks left on the ground, the flying ones had ticked just a fraction more slowly, too small to notice in daily life, but enough to prove that speed truly affects time. Then there's the twin paradox. Imagine one twin blasting off on a high-speed space voyage, while the other stays home. When the traveler returns, they're younger than the sibling who stayed behind, not from cosmic skincare, but because time itself moves slower for them. Gravity's grip on time. Einstein didn't stop there. In 1915, his general theory of relativity showed that gravity also distorts time. Massive objects curve space-time like a heavy ball on a stretched sheet, and time flows more slowly, closer to the mass. This effect has been measured on Earth. Atomic clocks at sea level tick ever so slightly slower than those at higher altitudes. Technically, your feet age more slowly than your head. GPS satellites deal with both effects at once, moving quickly, which slows their clocks, while being farther from Earth's gravity, which speeds them up. Engineers constantly adjust their timing to keep navigation accurate, or your phone's map would drift kilometers off course in minutes. Direction of time. Einstein revealed that time isn't a rigid, universal river. It's flexible, woven into space itself and personal to your position in motion. But that raises another question. Why does time seem to move only forward? Most physical laws work just as well in reverse. Two colliding particles could be rewound, without breaking the math. Yet in everyday life, eggs don't unbreak, ashes don't reassemble into books, and we remember yesterday, not tomorrow. This one-way feeling is explained by the arrow of time, tied to the second law of thermodynamics. In a closed system, entropy, the measure of disorder, always increases. Things naturally go from orderly to messy. You can scramble an egg, but unscrambling it is astronomically unlikely. That tendency toward greater disorder gives time its direction. A low-entropy past becoming a high-entropy future, and it leaves us with one of the deepest mysteries in cosmology. Why did the universe start in such an improbably low-entropy state? If the universe keeps getting messier, there must have been a moment when it was perfectly neat. Current thinking, right after the Big Bang, things were smooth, uniform, and low in entropy. Over billions of years, gravity and expansion stirred the pot galaxies formed. Stars died spectacularly, and yes, socks vanished mysteriously. Why the cosmos began so tidy remains one of physics' big open questions. Time has multiple arrows, and interestingly, they all point the same way. The psychological arrow we remember the past, not the future. The causal arrow causes happen before effects. Cosmological aerospace keeps expanding, galaxies drift apart. All these are tied to entropy increasing, guiding time's one-way march. But not everyone thinks time is fundamental. Some scientists believe the arrow of time only emerges when complex systems like us observe change. In quantum mechanics, time often feels like a background clock, not an active player. The Schrödinger equation moves quantum states forward, but time itself stays fixed. That's very different from Einstein's relativity, where time stretches and bends. Try combining quantum mechanics with relativity, and you hit the problem of time. In certain quantum gravity equations, time simply vanishes. No past, no future, just an endless now. This leads some to think time might be like temperature. It doesn't exist at the smallest scale, but appears when many systems interact. Others point to quantum entanglement. Maybe time's flow emerges as the universe becomes more tangled. And then there's the many worlds idea. Every decision splits reality into parallel timelines. In that picture, time isn't a river. It's an endlessly branching tree. Still, in daily life, time feels steady because quantum chaos averages out. Our brains are wired to see cause and effect, turning existence into a story. Whether time is an illusion or a fundamental ingredient, it's the thread we use to weave meaning into our lives. Humans are natural storytellers. We weave moments into memories, dream about the future, and build our identity across past, present, and what's yet to come. Whether or not time is truly fundamental, we live as if it is. But quantum physics hints that beneath this familiar narrative, time may be less a steady tick and more an unfolding of possibilities. Probabilities reshaping reality with each passing moment. Beyond clocks and calendars, time is also running inside us. Our bodies operate on internal cycles known as circadian rhythms, roughly 24-hour patterns that guide sleep, appetite, mood, and more. These rhythms exist in nearly all living things, from humans and animals to plants and even some bacteria. The master timekeeper in our brains, the suprachiasmatic nucleus, SCN, sits just above where the optic nerves cross, perfectly placed to read cues from light. Morning sunlight signals the SCN to adjust hormones and temperature, while melatonin rises at night to help us sleep. Without light to reset us, our natural rhythm drifts slightly each day. A problem light solves until jet lag or artificial lighting throws us off. Screens and blue light delay melatonin release, nudging bedtimes later. While genetics also shape whether we're morning larks or night owls. These rhythms don't just affect sleep, they influence metabolism, immune response, athletic performance, and even how medicines work. Plants, animals, fungi, all keep their own versions of time tied to cycles of light and dark. So when you feel drowsy at 3 p.m. or suddenly alert at night, it's not random. It's the quiet pulse of biological time, an ancient rhythm still keeping beat inside you. Your body's been moving to an ancient hidden rhythm since long before clocks, calendars, or triple-shot lattes existed. Our ancestors relied on it to stay alive and rested. Even now, alarms and schedules might try to boss us around, but deep down, we're still quietly sinking to the sun. And yet time seems to have its quirks. A holiday week can vanish in a blink, while 10 minutes in a dull meeting can feel like an eternity. That's psychological time, the strange way our brains measure moments, often ignoring what the clock says. When we're having fun or absorbed in something, our focus leaves no space to track seconds. They simply slip away. Boredom, on the other hand, makes every tick of the clock drag like taffy. Memory also plays tricks. A week of new adventures might feel short while you're reliving it. But looking back, it seems long because your brain filled it with vivid moments. Routines do the opposite. Days blur together and years feel like they've flown. Emotions bend our sense of time too. Fear or intense excitement can make moments seem slow. not because they actually are, but because we record more details and remember them as stretched out, even mindfulness. When we stop counting minutes and just exist in the moment, can make time feel like it's gone altogether. Kids live in their own version of time until they're trained into the adult schedule. Anticipation, whether it's excitement or dread, can stretch the days leading up to an event. And then comes the sci-fi question. Can we travel through time, one direction, the future? Yes, we already do it. Thanks to Einstein's relativity, moving near light speed slows your time compared to everyone else's. Astronauts aboard the ISS return to Earth a few microseconds ahead of the rest of us, the past. General relativity allows for mind-bending possibilities, like loops in space-time or wormholes. But making them real would require conditions far beyond anything we can reach, at least for now. So while physics might keep the door to time travel cracked open, most of us are stuck with the only machine we've ever had for moving through time. Our own minds shaping every second through memory, emotion, and attention. If one mouth of a wormhole were taken on a near light speed trip and brought back, its clock would tick slower than the one that stayed put, stepped through, and in theory, you'd pop out in the past. Of course, that's the sci-fi movie trailer version. Reality throws up some giant roadblocks, like the fact we don't even know if wormholes truly exist, might snap shut instantly. And keeping one open would require exotic negative energy we've never been able to produce. Even if we solved all that, going back would tangle us in paradoxes. The most famous? The grandfather paradox. If you stop your grandparents from meeting, you'd never be born, which means you couldn't go back to stop them in the first place. Philosophers and physicists have offered workarounds. Fixed timeline block universe. Every moment already exists. If you travel back, you were always meant to be there. You can't change anything. You just play your pre-written part. Many worlds change the past, and you branch off into a new universe, while your original remains untouched. No paradoxes, just parallel histories. Novikov principle. The universe prevents paradoxes. Something always stops you from altering events in a way that breaks the future. Still, it's all theoretical. No time machines, no verified travelers. Despite internet photos of oddly dressed visitors, maybe travel is only possible to the point when the first machine is built. Maybe time tourists blend in, or maybe it's flat out impossible. And perhaps that's a good thing. Our inability to rewind might be what makes life meaningful. You can't cut and re-edit existence like a video file. You move forward, moment by moment, with all the unpredictability that gives life its depth. But that leaves us with one last stranger question. Does time even exist? We tend to think of it as a flowing river. Past behind, future ahead. It's presentism. Only the now is real. But Einstein's relativity gives us eternalism, where time doesn't flow at all. Every moment, childhood, old age, and everything in between, exist together in a four-dimensional block universe. In that picture, you're not moving through time at all. You're simply a fixed thread woven into the whole tapestry of space-time. Comforting, maybe a touch eerie. This idea flows naturally from Einstein's relativity. Now, ice and tea universal, two people moving differently can disagree on what counts as the present. That means there's no single cosmic clock ticking for all. Quantum gravity takes it further. In certain equations, like the Wheeler-DeWitt equation, time doesn't even appear. The universe, in that sense, could be timeless. So why does it feel so real? One possibility. Time isn't a built-in feature of reality at all, but something that emerges, like temperature from molecules or waves from water. Our brains may simply stitch together changes into the illusion of a flowing moment, much like still frames in a movie becoming motion. Physicist Julian Barber pushes this further, imagining reality as a collection of frozen nows, timeless snapshots of the universe. We experience movement because of the way these nows are arranged and the memories they contain, like a cosmic photo album we flip through. But others argue that even if time is emergent, it still has teeth. Clocks tick, planets move, atoms decay, all in sync with one another. Time, then, is real in the way a story is real. It gives order to events even if the paper it's printed on is stranger than we understand. So, does time exist? It's maybe not as a flowing stream or a hidden metronome, but it exists in our experiences, our cultures, our physics, and our hearts. It's the shape behind change, a reminder that moments are fleeting and precious. And here we are at the end, or simply at another page in an endless book. We've wandered from sundials to relativity, from paradoxes to timelessness, and now you're just a little further along your own path than when you began. So, in your own corner of the world, what time is it now? And does that number really matter, or is it simply one more story we tell ourselves before drifting into rest? Sleep well, traveler.